Okay, hello everybody. Good morning. I mean, I say good evening. Right. I hope.
Good evening, sir.
Good evening. Good evening. Right. I see how many people. I see 11. Right. Okay. I think it's a good number to start with. Right. Excuse me. So yeah, I think we can start. Right. So let me share my screen. Okay. Okay. So guys, do you want to go through whatever we saw last class? We saw only photoelectric effect. Do you want to go through this or we can continue? Yes. Any suggestions? You want to continue what is mean? You want to see what we saw last class? That is the photoelectric effect, and then we'll continue, or you directly want to continue? What do you want?
Sir, we can continue, sir.
I hope everybody's okay with it, right? So if at all anybody wants,
Yes.
please tell. Okay, fine. So if at all anybody wants me to repeat anything, please ask me. You are always free. I mean, you're always free to. You can always feel free to ask, right? Okay, fine. Let me and then I'll go to the new concepts today. So today is 31st. 3107, and before that or 11th, right? Okay, fine. So if you can remember, people, right, we started with the simplest of things. We started with what is the Dalton's theory, what is Dalton's theory, and how Dalton's theory was disproved because of various subatomic particles getting discovered. J.J. Thomson discovered electrons, Goldstein discovered protons, Rutherford discovered nucleus, right? And there was one more guy who discovered neutrons, right? So based on all this stuff, then came your Bohr's theory, because obviously the Dalton was not able to say, he said that atoms are indivisible. We went to J.J. Thomson's theory. There was electrons and Rutherford's model, nucleus, and then we went on to see your Bohr's model. We saw how it works, what are the postulates, what are the drawbacks. Drawbacks are very, very important because there are a lot of stuffs there. Heisenberg's uncertainty principle, de Broglie's wavelength, Zeeman effect, Stark effect. It is going to work only for single electron species, right? Then we went on to see this photoelectric effect. These are the things which you saw till now. Okay, now what are we going to see today is the most important point, most important thing. I'm just going, and this you're going to use till the end of your life. I mean, if at all you're going to continue with chemistry, right? So this is all. This is going to give you the very basic requirement for us to write the electronic configuration. Till now, you know how to write the electronic configuration. Say if I have an atomic number, say of 12, you will write it as 2, 8, 2, right? So like, first, say you follow this formula 2n squared, all these things you follow in your lower classes, right? So we tell that I have nucleus, I have this called, this is my K shell, this is my L shell, this is my M shell, so on and so forth, right? So this is how you have been, writing electronic configuration. Okay, but today we are going to move into an entirely different way of writing electronic configuration. Obviously, further you have to understand what exactly is the atomic model which is given to you, right? Once you understand the theory part, once you understand the model, what is the science behind it, then putting electrons and all these, whatever you're going to see is going to be very, very easy. Okay, so the task for us today is to see this quantum mechanical model of an atom. Okay, right? Now, the see, there is some, I don't know whether you have been hearing these terms. You must have hearing this term quantum mechanics, quantum. You have been using this term quantum so for a long very time. We know what exactly is a quantum now, right? Quantum means, when I say a quanta, is nothing but a packet of energy, right? So this and all we saw in your Planck's quantum theory. Okay, so this quantum mechanical model was actually derived, I would say the basic idea, like basic idea was from, I would say the basic idea was derived from Bohr, and then Heisenberg, uncertainties principle, and obviously he also took de Broglie's. Okay, and who's the scientist behind this quantum mechanical model is the Schrodinger. Okay, very famous guy, right? Schrodinger's cat, Schrodinger's, like if you go to college first year, right, you will be studying engineering physics. That's a subject. Okay, so there you'll study more about what work Schrodinger did. There's something called a Schrodinger time dependent equation, time independent equation, so on and so forth. So in depth, you can study about this, right? But we are going to restrict ourselves to very basic concepts, and certain things I will tell you that this is how it works. And if you ask me to explain, sir, how or why not, why this, that questions, most of them I will try to answer, coming to your level and try to answer. But if I tell you that no, it is not possible, it is beyond the scope of your level, you have to trust me with that. Okay, right, fine. So as I told, Schrodinger was the one who gave this quantum mechanical model, and this is the current one which we are using. The atomic model, how that atom looks and stuff, right? So this is what we are currently using, right? And that is given by Schrodinger. And he took all the ideas from Bohr, Heisenberg, and de Broglie. And obviously, you understand what Bohr's, obviously, he took the concept of orbits, the electrostatic force, and so on and so forth. Heisenberg, he took that the condition of probability. This is very important. Okay, so from Heisenberg, he took the condition of probability. He said that obviously we know what Heisenberg said, right? No two conjugate quantities can be measured simultaneously with 100% accuracy, right? So all that thing he take into account, and obviously he took the dual nature from de Broglie. Okay, so all these things he combined, right? Okay, so what exactly is this model, right? Or what I would say, right? This Schrodinger, what he said, right? This particular model, I will call it as a probabilistic model. Everything is only probability, saying that, say, there is a chance of doing this. There is, say, 70% chance of that happening, 40% chance of that happening. Say something like that. It is purely probabilistic model. Okay, right. So now what am I going to do in this, right? So if I have to make it very simple, okay, so please understand there is this term called as psi. Okay, this is the symbol. Okay, there is this term called as psi. Okay, now this psi is what is called as work function, and this work function and the work function you saw yesterday are entirely different. Okay, this work function is psi. Okay, now as such, it has no physical meaning. Okay, as such, it has no physical meaning. Okay, but please understand, and this psi is not a number. Okay, this is a function, like say how you have sine, cos, you write sine of something, cos of something, log of something, right? So these are operators. Correct, these are functions. You put some number here, and that the sign of that number, cos of that number again will be a number, right? So like that, you write psi of x, something like that. Okay, you can understand this is a function. Hope you understand the difference between a number and a function. Okay, so this psi is what is called as work function, and I told you that it has no physical meaning as such, right? Now how am I going to use it is very simple, guys. Okay, so now when I square this function, right, when I make it psi squared of x, okay, when I square this function, what Schrodinger told is that we can get the probability of finding an electron in a given volume. Okay, so hope you understand what I'm trying to say. Psi squared of x, right? So if I apply this function in a given volume, say this is some volume, okay, there are so many empty spaces, there are so many other things, but I'm going to say, or I'll put it like this. This is a big circle, and I want to find whether in this particular volume I have electron or not. Okay, this is the entire atom. Assume the entire big circle is the atom. Okay, now I want to take a very small volume and check what is the probability or what is the chance that electron might be there. Okay, so for that is given by the psi squared of x. Say this psi squared of x function, if you apply in this particular small volume, it will tell that, okay, 60% chance that electron might be there, or 70% chance that the electron might be there. right? So hope you understand what is the use of this psi squared of x, right? Psi of x has no physical meaning, but if I square this function and use it a particular volume, a small volume inside the atom, it is going to give you the probability of finding the electron in a particular volume. Okay, in that particular volume, what is the chance that I can find electron? Okay, right, fine. Now, one more thing, what you have to understand here is that, okay, like he also gave the concept of orbitals. Okay, he also gave a concept called as orbitals. Okay, now before we move on to see what these orbitals are, okay, so first what you have to understand is this entire model, right? This entire quantum mechanical model which you're talking about, right? It is actually, I would say, okay, or we'll put it in this way. When I go to Bohr's, right? He said the orbits are there. We even call it as stationary orbits, if you can remember. Right now, this stationary orbit concept is there here also. Okay, but what your Schrodinger said is that these orbits are in the form of waves. Okay, these orbits are in the form of waves. Okay, but how is it in the form of waves? Say, if I have to tell you, like, say, assume that this is the nucleus. Okay, say the first shell, first orbit I want to draw. Generally, what we do, we put a circle, right? This cannot be the wave. But say, if I want to represent it, I will put it like this. This is the first shell. Say second shell will be something like any random wave. You can understand, right, what I'm trying to say. It is not a definitely, say, this is not a definite path, right? Say, for example, if I want to go from Chennai to Bangalore, right? Say, I know what is the exact route, right? I know the road goes through this way. I know the exact route. But that is what the same thing happens with your Bohr's model. Exact prediction. In this place only the electron can be present, right? But what your Schrodinger said is that these orbits are going to be treated like waves. Okay, and you can understand, you can connect the concept of waves with the concept of probability. Hope you understand, right? Say, like, say this is point A, and say here is some point A. Now this point A and this point are entirely different, isn't it? This is a perfect circle, and this point A, say this is at some 2 seconds, first 2 seconds the A point is here, but after this time this would have again changed its state, and say the point A is there after, say, 5 seconds. I'm just giving you some random numbers. Okay, so all you have to understand is that the place where the electrons are present, right, they are in the form of waves and not exactly a place where the electron stays. Okay, right? And second thing is, this entire model is entirely based on probability, not like saying that for sure this is going to happen. No, we are not going to do that in this model. Okay, fine. Now this we understood, right? So what you have to understand in this term, orbitals. Okay, now what you have to understand is, people, orbits, I will call them as shells, you all know, right? Now each orbit has some subshells, or each shell, I will say, will have some subshell. It's like this. Say, look at this. This is the nucleus. Okay, now say this is the first shell. Okay, now if you look at with your, say, not so powerful microscope, no, microscope shouldn't be the use. Say, assume that some microscope is able to visualize this. Okay, say you have a more powerful microscope and you have, say, a less powerful microscope. Hope you're understanding what I'm saying. Okay, there are two microscopes. One is a very powerful microscope, even smallest of things it will be able to see. Another microscope is there which is not that strong. Okay, say now you visualize this particular arrangement which you see here with a less powerful microscope, right? So if you if you see it with a less powerful microscope, you will see obviously only one orbit, that this term, the first shell is what will you see, right? But if you zoom in, or say if you try to use a more powerful microscope, what will you understand is that this orbit, if I just zoom it, okay, I have to go, if I just do it like this, if I just zoom it, okay, you will see that this orbit is made up of so many number of small lines like this, or small spaces like this. Okay, so that from this, what you understand, this is not one single thing, right? It is made up of so many things like this. Okay, or in other words, orbit is there, but in each and every orbit you have some subshells, or each and every shell you see only the shell with a less powerful microscope, but if you use a more powerful microscope you are going to see the subshells also. I hope you understand. If we zoom this and visualize this, you will see this kind of pattern. Okay, right? So
Sir,
yeah, please tell me.
sir, so these subshells are also in the form of wave.
Yes, the subshells are also, this orbitals are also, where is it? Orbitals, did you write anything? Okay, the subshells or orbitals are also in the form of waves only. Okay, right. So what I'm trying to understand, like see, say we talk about the K shell, L shell, M shell. Okay, now say K shell will have one psi of x. This psi tells me what is the wave pattern. Okay, this psi, I told you that doesn't have any physical meaning, right? So what it just tells me is that how the wave pattern looks. Okay, say it can be a sine wave, or it can be some this kind of wave. Okay, so what kind of wave is there is denoted by this psi of x. Okay, so okay, will have one type of wave. This will say have psi 2 of x, this will have psi 3 of x, right? Also obviously each and so K shell will have its own suborbits. They will again have different wave functions like this. Okay, so both the shells or orbits, or say subshells or orbitals, all of them are in the form of waves only, right? Okay, now this we understand. Now what we have to understand is, okay sir, K shell has how many subshells, L has how many subshells, M has how many subshells, and in each subshell how many electrons I can put, right? All these are the questions which come to your mind. Okay, because till now we know how to fill in this. Say I'll put 2 here, 8 here, say 18 here. I actually not 18, 8 only here. Next we'll have 18. I already know how to fill them. Okay, now to understand these numbers, right? This 2, 8, 18, I mean 2, 8, 8, 18, all these things are not going to change. Okay, now this 2 electrons, I would say instead of putting in the shell, they will actually be in the subshell, right? So many subshells come together to form a shell, or in other words, so many orbitals come together to form an orbit. Okay, right. Now what I have to understand is this 2 electrons or 8 electrons or 18 electrons or whatever it is, in which subshell are there, and how, like if I have how many different types of subshell I have, right? And each subshell, what is the maximum number of electron I can place? All these are the questions which should be living in your mind right now, right? So we will try to answer each and every question which is possible from you. Obviously not the physics part of this, obviously not, but the electronic configuration part, yes, we will try to answer all the questions possible. Okay, right, fine. Now I told you that this psi squared of x, as I said, psi of x doesn't have any physical meaning. Psi squared of x is going to give you the probability of finding the electron. Okay, now this x, what you see here, right? This x is what you see here. These are the input values, right? These are the input values, right? Now, what are these values? Based on this value only, this entire thing will change. Say if I put the value as x as 1, there'll be some value. If I put x as 2, there'll be some other value. So what values you will put here, right? What is the input value you give to this psi squared of x, right? Now that input values, guys, right? That input values which you give to the wave function square, right? The input values which you give are what are called as quantum numbers. These are what are called as quantum numbers. So basically, this psi squared of x we write, or psi of x, whatever we write, this x are nothing but this quantum numbers. You're going to give the input as the quantum number, and according to the quantum number, this value is going to give you the probability of finding the electron in that particular place. Okay, right, fine. Now, there are going to be 4 quantum numbers. Okay, the quantum numbers are of 4 types. Okay, first one is what is called as principal quantum number. Second one is what is called as azimuthal quantum number. Third one is what is called as magnetic quantum number. And at last, the last one is what is called as spin quantum number. Okay. Now, each and every quantum number is going to answer one question. Okay. Each and every quantum number is going to give you one data about where the electron is exactly present. Obviously, we'll not be able to tell the electron is exactly present. Obviously, it is going to give you the probability of finding the electron in a particular space. Okay. But different questions are answered. Okay, we will try to understand what are the questions answered and how are these numbers and how, like, say, what is the maximum value, minimum value, say azimuthal quantum number is going to depend on the principal quantum. All these things we'll see now. Okay, so till now, like, there's only few points you understand, people. First point is that there's something called as psi, right? Psi is called as wave work function. Okay, so for different orbits, K shell, L shell, M shell will have different types of waves. Okay, now those different types of waves are given by the psi 1, psi 2, psi 3, so on and so forth. Second thing, psi only gives the is about the wave pattern. It has no physical meaning. But psi squared of x, if I square that function, wave function or work function, right? Now that is going to give me the probability. Okay. Now, this probability, what are the input value? Obviously, for any function, there'll be some input values. Now, these input values are nothing but the quantum numbers. And there are 4 different quantum numbers, right? And one more thing what you have to understand is that each orbit is made up of so many number of orbitals, okay? Or I would say each shell is made up of so many number of subshells. Right? So these points, if you understand, then we can easily go into quantum numbers. Till now, everybody is fine, people. Can I get a yes? Till now, any problem? Everything is okay? Any difficulty? Anything?
Yes, sir.
Okay, I suppose yes, everything is, yeah, cool. Right? Anything if you have, you always need to ask. Right? Okay, cool. So we'll first concentrate on what is this principal quantum number. Okay, right. The first one is my principal quantum number. I'll write Q number, quantum number. Okay, and it is denoted by the letter N, small n. Okay, right. Now, I told you that each and every quantum number is going to answer one question regarding the place or probability of finding the electron, right? So this principal quantum number is going to tell me what is the orbit number, orbit or main shell. That is the shell, right? Main shell or shell, because we just differentiate main shell and subshell, something like that. Okay, so what is the orbit or main shell number? That is exactly what it gives, right? So now this n value can start with 1, which obviously it should be only integers, right? It should be only integers, because obviously an orbit number, a stationary orbit number can be 1.5. Can I have 1.5th orbit? No. 2.3 orbit? No. All I can have is first orbit, second orbit, third orbit, fourth orbit, so on and so forth, right? So n value can be 1, 2, 3, so on and so forth. It can be up to any integer. Okay, right? So basically, this is what is this we already know, right? This first shell, second shell, third shell, I already know how it is. Right? So it's very simple to understand. From the question, this thing is we can understand. Principal quantum number gives you the answer to this question. What question? What is the orbit number? Whether it's the first orbit is electron present, or in a second orbit electron is present, whether in third orbit electron is present. Okay, and one important point I forgot to tell you. Right now, this quantum numbers we tell, right? I'm sorry. Right, this quantum numbers we tell, right? These quantum numbers are going to be given for every electron, right? For every electron, right? You are going to give all these 4 quantum numbers. Okay, say for example, if I talk about the principal quantum number, right? Say I want to know how do I put the question? Say I have hydrogen. Okay, hydrogen I know has only 1 electron. For this 1 electron, what is the principal quantum number value? If I ask you, what will be your answer to the question? Again, I repeat, hydrogen has this only 1 electron. So for this 1 electron, what is the principal quantum number value? What will be your answer?
1.
Absolutely. Obviously, the electron cannot go anywhere. It has to be there in the first shell only, right? Okay. Now, if I ask you, I have lithium. Lithium has, say, 3 electrons. Okay, I'll write it as electron 1, electron 2, electron 3. Okay. Now, what is the principal quantum number of electron 3, third electron? Lithium has an atomic number of 3, right? That means it has 3 electrons. 2. Right? Easy. Exactly. It's correct. Now, how do you write the configuration for lithium? I write it as 2, 1, right? Now, this is n is equal to 1. In n is equal to 1 itself, I have 2 electron. So obviously, third electron here will be in n is equal to 2. Right? Oh, I hope everybody is able to understand what this n value says. Okay, it tells me for that particular electron is there in which orbit or which main shell. That is what is given by principal quantum number. Okay, maybe we ask you one more Dow in this thing. Say sodium, the 11th electron. Okay, what is the n value? Sodium atomic number is 11. Okay, right? I want to know for the 11th electron, last electron, what is the n value? Okay, I think one second. Okay, it's correct, right? Fine. I hope everybody understood how is it 3, right? How do I write it? The electronic configuration. Forget about the orbitals and subshells. How do you write it? 2, 8, 1. This is how you write, right? So this will be n is equal to 1. These 8 electrons are n is equal to 2, and this one electron is in n is equal to 3. So I asked you, this is the 11th electron. For 11th electron, what is the n value? Like it's basically 3. Why? Because it is the third shell. This is my third shell, right? Okay, I hope everybody is able to understand whatever is happening here. Okay, right, fine. So that is about the principal quantum number. It tells me what is the main shell number. Very, very simple. Okay, and it can take only integer values starting with 1, not with 0. It cannot start with 0, people. You always start with 0. Okay, next quantum number is my azimuthal quantum number. Okay, and is denoted by the letter L, small l. Right? Okay. Now, what is the question this is going to answer? Now, this answers the question of what is the subshell. Okay, we already told, or I would say, what is the orbital? Okay, right. Now, before we move on to see how is it going to answer the question, people, please understand there are 4 types of orbitals. Okay, there are 4 types of orbitals. One is, or 4 types of subshells. Okay, so one is what is called as s orbital. The other one is what is called as p orbital. The other one is what is called as d, and the other one is called as f. And still research is going on to find this g orbital, but this you don't have to worry. Don't worry about it. Okay, these 4 orbitals are very, very important. Okay, so if there's someone asks you what are the 4 different types of orbitals in any atom for that matter, right? You have to say that I have SPDF, right? I don't know whether when I was a kid I used to watch this Power Rangers. Do you still watch Power Rangers, people? Is it still coming? Is it still coming? Used to watch. Okay, so obviously you know SPD, right? So this SPD, remember it as SPD force. F represents force. Okay, so I think it is what SPD full form is speed patrol data. It was something, right? What is the full form of SPD in that Power Rangers thing? Anybody remembers? Okay, even I don't remember. Anyways, so what you have to understand? No problem. No problem. Excuse me. So this
Space Patrol Delta.
Space Patrol Delta. Amazing, amazing. Right. Cool, cool. So yeah, so this SPDF, you remember it as SPD force. Okay, so G still research is going on. That's a like again very higher level, even for me, right? This still research is going on. So I wanted to understand this 4, right? What are the 4 different types of subshells? SPDF. These are all the 4 types. Okay, now see if you ask me this question that, sir, K shell, the first shell, basically K shell will have n is equal to 1, right? L shell will have n is equal to 2, right? So will K have all these 4, right? And say L will also have all these 4? The answer is no. Okay, now which orbit, right? I'm telling you which main shell contains how many subshells. For example, let me tell you this. When I have K shell, I have only S orbit present, right? But when I go to L shell, S and P are present. When I go to LM, I have S, P, D, all three are present. And when I go to N, S, P, D, F, all four are present. And from next shell onwards, all the other fours are present. Okay, again, you don't have to mug up anything here. Do not mug it up. Do not mug up anything here. Right. So what I'm trying to understand, what I'm trying to make you understand is that each and every orbit, it's not like all orbits will have all the four suborbitals or subshells. Okay, there one say K shell is going to have only S, L, the second shell will have S and P, third will have SPD, fourth will have SPDF, and from O shell and all, everything will have four subshells. Okay, right. Now, how are we getting this? Whatever I told you here, right? K will only have S, L will only have S and P. All this comes from this particular quantum number. That is my azimuthal quantum number. Okay, right. Now, what you have to understand here is that this L value, again, this L is going to be some value. Okay, now this L value depends on N value. Right, this L value depends on the N value, and how it depends, let me tell you. Right, so L, right, can start with 0. Okay, L, like how I said last time, N will start with 1 and it can go, it can be any other integer, positive integer. Right, like that, L will start with 0, say it can go to 1, but the maximum value with the particular L value can be possessed is N minus 1. Okay, say it can start with 0, 1, 2, 3, but the maximum value the L, a particular L can have is N minus 1, right? So what is the range of this? It's basically 0 to N minus 1. Okay, in between this range, only the L value exists, right? Now it's very simple for me if you understand. For N is equal to 1, that is the first shell or the first orbit. Right, now tell me what are the possible L values. Now looking at this data, now I told you that
0.
Only possibility is 0, because the maximum value the L can possess N minus 1. Now N is equal to 1, 1 minus 1, the only value possible is 0. Right, same way if I take L is equal to, sorry, N is equal to 2, now tell me what are the possible N values.
0 and 1.
Absolutely, right? I told it can start with 0 and the maximum value is N minus 1. The N value here is 2, second shell we're talking about, right? So obviously 0 and 1 are the possibilities. Same way when I have N is equal to 3, L can be 0, 1, 2, and say N is equal to 4, L value can be 0, 1, 2, 3, it keeps on going like this. Okay, now what does this, so you understand, right? For N is equal to 1, I have L is equal to 0. For N is equal to 2 also I have L, one of the values of L is 0. For N is equal to 3 also one of the values 0. And N is equal to 4 also one of the values 0. Same goes with say 1. L value of 1 exists for second shell. L value of 1 exists for, okay, L value of 1 exists for third shell. L value of 1 exists for fourth shell also. Right. So what you have to understand here is that each and every value of azimuthal quantum number represents one subshell. Okay, each and every value of azimuthal quantum number represents one of the subshells. Now, how do they represent this? Let me tell you. It's very, very easy. L is equal to 0 always represents S subshell. Okay, L is equal to 0 always represents only S subshell. L is equal to 1 always represents P subshell. L is equal to 2 always represents D subshell. L is equal to 3 always represents F. And say if at all you have L is equal to 4, that means it is G. Okay, this you have to remember. Okay, L is equal to 0 means S, 1 means P, 2 means D, 3 means F. Right, now if you understand this particular point and this 0 to N minus 1, then whatever I wrote here, right? So I told you that K shell will have only S, L will have only S and P, M will have SPD, and N will have SPDF. How this came is based on this, what you saw here, right? and the 0, 10, minus 1 factor. Right. Okay. Let me understand how this came. Right. So for n is equal to 1, right, that is my K shell. What is my L value? L value is 0. The 1D possible L value is 0. And I told you L is equal to 0 corresponds to what? Yes. Right. So this means the first shell, that is the K shell, has only S. That is done. Right. Now, when I go to n is equal to 2, now I have possibility L value possible to be 0 and 1. Now, I already told you 0 corresponds to S and 1 corresponds to T. Right. So that's what I told. L will have S and T, or n is equal to second shell will have S and S subshell and T subshell. Same way, n is equal to 3 will have 0, 1, 2. Now I know 0 corresponds to S, 1 corresponds to T, and 2 corresponds to D. Now you can look here. Third shell, that is the M shell, will have all S, P, D, all the 3 orbitals. Same way I look for n is equal to 4, you'll get 0, 1, 2, 3. 3 will represent F. Okay, right? And any, okay, I hope everything is clear. Right. Now, how do I represent it? Okay, now we understood based on the L value how the orbitals are there, but how am I going to represent it? Okay, now you represent it like this. You represent it like, say for example, I want to talk about, say, now I ask you this question, right? Say S subshell is there in first shell, or S orbital is present in first orbit, and say in S orbital is present in second orbit also. Now, how do you differentiate between these two S orbitals? The same can be like this. P orbital is present in second shell also. P orbital is present in third shell also. How do I differentiate this? Both are P subshells, right? But how do I represent it? What is the difference between them? How is the representation is to be different? This is how it is going to be. Okay, this is how, say for example, I want to represent the S in the first shell. Okay, I want to represent the S orbital in the first shell. Now, how do I write it? It's like this 1s. Okay, that means what? This 1 represents the principal quantum number n, which shell it is. And this represents obviously what is the subshell. Okay, right. Now, say if now same way I can represent this. Say I want to represent the S orbital of second shell. Right now, how do I do it? It's very simple. I write 2s. 2 represents the shell number. Obviously, S represents the orbital number. Orbital. What is the orbital? Right. Now, answer this question. Do I have if I write 2D? Is this correct? Okay, I don't want any answers on the mic. Can everybody please participate in the chat box? If you feel that it is right, put yes. If you feel that this 2D is wrong, then you put no. Can I go to the chat box? Can everybody go to the chat box? Yeah. I think so. A lot of answers are coming. No. Okay. Good. Okay, yes, exactly. Like only 3D is possible, 2D is not possible. Absolutely. I think everybody is following. Wonderful. Great going, people. Yeah, please tell me.
Sir, I have a doubt.
Yeah, tell me.
Sir, so usually SPDF is the notation to represent orbitals or subshells. Both
orbitals and subshells are same.
Sir, aren't they different actually?
I mean, subshells, like what to say, like colloquially speaking.
Inside subshells, orbitals are present, correct?
Inside subshells, orbitals are there. Yeah, but in most of the textbooks, and most of the people, however they try to explain you, they will explain you that actually orbitals and subshells are almost same, right? When I say orbitals, I bring in the wave nature. But when I say subshell, I don't bring in the wave nature. That is the main difference there. Do you understand what I'm trying to say?
Yes, sir.
Okay, there is not much difference there. Like even if you refer to any good textbooks also, they will actually use these terms alternatively only, orbitals and subshells. I don't have to worry about it. Don't worry about it. Right? At least for your level, you really don't have to worry about it. Okay, right. Fine. So this 2D doesn't exist. Why 2D doesn't exist? Because from this, I can understand that n is equal to 2. For n is equal to 2, what are the possible n values? L values 0 and 1 only. That means s orbital is possible, p orbital is possible, but where is 2? Only if I have 2, then I have a d orbital. So this is not possible at all. Same goes with 1p. Not possible, right? Because first orbital n is equal to 1 can have L is equal to 0. That is only s orbital. Okay, right? So like this only we have to, okay. So that's how we represent also. Okay, you start with the principal quantum number and write the subshell, right? So 1s means the s orbital of the first shell, 2s means the s orbital of the second shell. If I write 3p and 2p, 3d, 4d, 5f, all these things represents different orbitals in different shells, right? This represents d orbital in the fourth shell. This represents d orbital in the third shell, something like that. Okay, I hope everybody is following. Everybody is okay with this, right? Okay, so that is what is my azimuthal quantum number, right? So principal quantum number tell me what is the main shell or the orbit, right? And azimuthal quantum number tells me what is my subshell or the orbital. And L value will depend on n value, and how it depends. Minimum value is 0, maximum value is n minus 1. Okay, so you cannot specify L value alone without knowing the n value. Impossible. Only if you know the n value, then you can speak about the L value. Right? I hope everything is clear. Everybody is following everything. Okay, right? Fine. Moving on. The third quantum number is called magnetic quantum number. Okay, it is denoted with the letter M, small m. What is the time? Okay, we have 45 more minutes, right? So the third quantum number is what is called as magnetic quantum number, denoted by the letter M. Okay, right. Now, this answers what question, if you ask me? Okay, right. Actually, so the question which you asked, the subshell and orbital, right?
So then there shouldn't be another quantum number itself, right?
Yeah. So the thing is, when I say S subshell, right? So I will tell that it has only one orbital, in the sense I have only one box. But if I go to P, don't worry guys, if you don't understand this, I'm just trying to, make myself enlightened, like between this concept of subshell and orbitals. But if I go to P, they say that when I say P subshell, that has 3 orbitals.
Yes, sir.
Right, it's like that. But again, but when you generally call, how do you call P? Will you call P a subshell, or when mostly 99% you call it as P orbital itself directly? Right now, how many such orbitals are there is the question. Now I have 3 P orbitals. Anyways, we don't have to go into the details, but yeah, it is little different, as you said. Right, it is definitely different, but you obviously can use them alternatively. Not a big deal at all. Okay, right, fine. So this magnetic quantum number, I would say this tells me what is the maximum number of electrons in a subshell. Okay, right? So what is the maximum number of electrons which can be placed in a particular subshell, in the sense that this magnetic quantum number is going to tell me in s orbital, maximum of only 2 electrons are possible. I'll write it like this: in s orbital, maximum 2 electrons. Whichever s orbital, 1s orbital, 2s orbital, 3s orbital, right? Whatever be the orbital, whatever be the s orbital, maximum 2 electrons can only can be accommodated there. Right now, P can have maximum of 6, D can have a maximum of 10, F can have a maximum of 14. It goes like this. Okay, now we'll try to understand how these numbers are going. I'm going to attain from this magnetic quantum number. How this explains how many electrons can be there in each and every subshell or orbital. Okay, right. Now what you have to understand, there is another way of putting this question. Okay, right. So another way of putting this question is, how many energy states, right? Now, actually, I think I have to specify the difference between I have to specify the difference between the orbital and subshell now. Anyways, I'll let you know, right? So how many energy states or subshells are there for a subshell? Okay, right, fine. So what you have to understand is, people, okay, now even though we actually alternately use orbital and subshell subsequently, right, but they are little different. Okay, now how they are little different is, let me tell you this. Okay, when I say S subshell, right, now I would say it has only one orbital. So what do you mean by only one orbital? You put only one box. Okay, see, all this, whatever I'm telling here, I'll explain how this comes from magnetic quantum number. I'm just trying to explain you the difference between subshell and orbital. Okay, right. But when I go to P subshell, right, I would say it has three orbitals, in the sense that you will put three boxes like this for P. Okay, for S, whatever be the S1, S2, S3, S, whatever it is, you will put only one box. I would say that because of that, I have only one orbital. Okay, P subshell has three orbitals, so I'll put three boxes. Same way, D subshell has 5 orbitals. So that means I will put 5 boxes like this. Okay, right. So what you have to understand is orbitals. Okay, let me put it like this. Orbits or shells, that is the first layer. Okay, second layer is my subshell. Okay, third layer is what is my orbitals, and this is where electrons are present. Okay, so because we will put the electron in these boxes, say for in this box I will put electron, in these 3 boxes I'll put electron, in these 5 boxes only I'll put electrons. Okay, so I would say orbitals are the place where the electron is exactly present, right? So you can understand it like this. The hierarchy goes like this. Subshells make up orbitals, subshells make up shells, and orbitals make up subshells. Or in other words, every orbit is made up of some subshells, and every subshell is made up of some orbitals. Okay, right? So orbits can be K, L, M, right? Subshells can be S, P, D, F. And in this, how many boxes are there? That is my orbitals. Okay, S has only one box, that is one orbital. 3 has 3 boxes, so 3 orbitals. D has 5 boxes, so 5 orbitals. Okay, right? Now this orbitals, that's I have mentioned this here also. This orbitals are also called as energy states. Okay, energy states or orbitals are basically the place where the electron is present. Okay, hope I didn't confuse you at all, right? Hope everybody understood the difference. There's a subtle difference between, subshell and orbitals, right? Subshell means SPDF, no doubt about it. But each and every subshell has how many boxes, how many places where the electron can be present. That is what is given by this term orbitals. Okay, but if someone asks you, give the exact definition of subshells and orbitals, it is actually very difficult. Okay, we will not be able to give exact definition as such, right? But still, I hope everybody is able to understand the difference between subshell and orbitals. Okay, now whatever the numbers I gave you, S subshell has only one orbital, P has only 3 orbitals, D has 5 orbitals. All this comes from this magnetic quantum number. Right, I hope you understand, right? It tells you how many orbitals are there for a particular subshell. So you will get the answer as for S it is 1, for P is 3, for D it is 5. Those are the answers you will get. But how are you going to? I'll tell you, right? And if you answer this question, that is how many orbitals are present for each subshell, you can easily answer this question also. What is the maximum number of electron which can be placed in a particular subshell? Okay, now how do I answer this question is by understanding this statement. Each orbital, or if at all you understand boxes or energy states, okay, each orbital or boxes or energy states can have only 2 electrons, only maximum of 2 electrons. Okay, maximum of 2 electrons. Now you look at this. Okay, if you understand this, each and every box, in every box, right? I have one box can have 2 electrons. This one box has 2, this one box has 2, this one box has 2. So totally 6. Same way, this one box, so only 5 boxes, 5 into 2, maximum 10. Okay, so now you can easily correlate what I wrote here. Right now, S, I told you can have maximum of only 2 electrons because only one box or one orbital. P can have a maximum of 6 electrons because it can have 3 boxes or 3 orbitals. And D, Y10 because I can have 5 boxes or 5 orbitals. Each orbital can have 2 electrons. Same goes with F. F will have basically 7. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Okay, so again, each box can have 2 electrons. Each orbital can have 2 electrons. Okay, right. Now we understood all the things. The only thing we didn't understand is how this M decides all of this. How is it decides? Okay, well, how is the number going to be? Right, now very simple, people. Now we understood what questions it is going to answer. If we understand how the values are M are there, then you will be able to easily understand other things. Okay, now M depends on L, obviously. How L depends on N, how the azimuthal quantum number depends on the principal quantum number. Same way, magnetic quantum number depends on the azimuthal quantum. Okay, right? So it depends on L. How it depends? This is how it depends. M value can have a minimum value of minus L and to a maximum value of plus L. Very, 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 very simple. Okay, right? Now, look at this. Say, for example, if I have L is equal to 0, that basically corresponds to S subshell. Right? Now, if I tell L is equal to 0, now I told you that M value can be between minus L to plus L. Can I say that the only possible value of M is 0? I don't have minus 0 and plus 0, right? Right? So when I have L is equal to 0, right, the only possible value for M is 0 because M value will be from minus L to plus L. Okay, now the 0 or 1 or 2, the value doesn't matter. How many values you have, right? How many values of M, that many orbitals. Very, very simple. Okay, there's no question mark here, right? So whatever is the number of M values, not the value of M. Remember this, okay? I do not care about the value of M, but how many M values are there? That is what matters now, right? So how many ever M values, that many orbitals. So what you understand from this is that when I have S subshell, that means when I have L is equal to 0, the only possible value of M is 0. Means I have only one value. So what? So only one orbital for S. That is what we have to understand. Okay, I have only one M value. That means I have only one orbital for S. Okay.
Sir?
Yeah, tell me.
Sir, does M depend upon N?
Obviously, right? Because indirectly, obviously, right? Because L depends on N and M depends on L. So indirectly, I can say that obviously M depends on N also. Right?
Sir, could you show how?
I'll tell you, right? So we'll just complete this and I'll show you exactly how exactly it works. I'll show you. Okay, fine. So when I have L is equal to 1, that means obviously know it corresponds to P subshell. Now, what are the possible M values? I told you it is from minus L to plus L. Obviously, all the in-between values also you have to take. It's not like only minus L and plus L. From minus L to plus L, right? So now L is the value. So minus 1, 0, plus 1. How many values are there? 3 values of M are there. So 3 orbitals are there for P subshell. Okay, that's why we represent it like this. 3. right? Same way, I represent S only with one box, right? Now, same way, if I can go for your L is equal to 2, that is my D subshell, right? Now, M value is again between minus 2 to, sorry, minus L to plus L. In this case, it will be from minus 2 to plus 2. So minus 2, minus 1, 0, plus 1, plus 2. How many values? 5 values of M. So 5 orbitals for D subshell.
Sir,
Yeah, tell me.
sir, what does the negative sign indicate?
Oh, nothing, nothing. That's what I'm telling you. The value is not important at all. Nothing. Right? All you have to understand is how many values are there. That is what is very important. Okay? These represents nothing actually. Right? So say I can actually put 0 first, minus 1 second, minus 2. I can do anything actually. This minus plus values actually doesn't indicate anything. All you have to understand is how many values are there. The what is the exact value doesn't matter.
So then I could
Yeah.
have written M value as M is equal to 1, 2, 3, 4, 5 because still the values are same 5, right?
But still, say the how you get 1, 2, 3, 4, 5, 5 values should depend on what shell are you talking about, right? So what shell, I mean, what subshell are you talking about? What subshell are you talking about comes from N value, sorry, L value, right? So it has to have some dependency on the L, right? So if this dependency is not there, how will you tell randomly that 1, 2, 3, 4, 5 exist? If I don't know anything about the L, which subshell I am talking about, I don't know, right? Then obviously I will not be able to give any M value for this. Are you able to understand? If I don't know what is a subshell, then how will you talk about how many orbitals a particular subshell will have? Makes sense, right? Right. Okay. And yeah, coming to the other question, how N, L, M, all those depends. Very simple, right? Say I start with N is equal to say 3. Okay, I start with N is equal to 3. Now, what are the possible L values? 0, 1, 2, because L value is from 0 to N minus 1. Right? Now, what are all the possible M values now? Now, for 0, it is 0. For 1, I have minus 1, 0, plus 1. For 2, how many? 5 values will be there. Right? What is that? Minus 2, minus 1, 0, plus 1, plus 2. Right? So now what do I understand from this? Is that I have third shell. Now third shell has L value of 0, 1, 2. That means 3S exists because I have 0. 3P exists because I have 1. 3D exists because I have 2. L value is 2. Okay. Now, how do I represent? Yeah, tell me.
Sir, then 2P will also have the same M value, right?
Exactly. That's the point, right? 2P will also have, it doesn't matter. When I have a particular particular L, obviously the M values will be same. And this particular L corresponds to a particular subshell. Say it's not, say, if at all you're going to have different values, say it's like this, say 2P, say right. 2P has 3 orbitals and 3P should have 4 orbitals. Doesn't make sense, right? Are you able to understand the point?
Yes, sir.
Right. So that's why if at all it's a P orbit, P subshell, it will always have only 3 subshell, irrespective of whether it's in whether the P is in the first shell or in the second shell or the third shell, doesn't matter. Okay. Right. So now we understood the M values, L values, N values. So 3S will have 1 box, 3P will have 3 boxes, and 3D will have 5 boxes. Right. Now, it again, as I told you, 2P will also have only 3 boxes. Why? Because the moment I have P, I know L value is 1. And the moment I have N value as 1, I have L values as, M values as 0, minus 1, 0, and plus 1. Hope you understand. So the thing is, N value is very, very important. Okay. From N value, you will know what are the L values, which will tell me what are the subshells, right? And for every subshell, M value is same, and that gives me the number of orbitals. Okay. So N value gives orbits, L value gives about the information about subshell, and M value gives the information about orbitals.
Sir, what does M value signify, like except from the number of orbitals?
Okay, it actually signifies the orientation, right? M value, actually this negative sign actually has some significance, negative and positive sign. So it talks about the orientation, right? M value also, you can actually mention it here. That is M. Yeah, magnetic quantum number, you can mention it here. It also talks about the orientation of the subshell, in the sense that, right, say this -1, say for example, if I take P, right? So P will have L value as 1, M value possible are -1, 0, and +1, right? Now, all of these values are going to this, all these are P orbitals. P subshells, P orbitals, right? But I can give different names to this. Okay. Now, different names are, I call it as Px, Py, and Pz. Okay. So orientation in the sense of to which axis the p orbital orients along. Now we'll also speak about what are the shapes. Then you will actually get more sense about what I'm trying to say here. Okay. So all now what you have to understand is to which direction or in which coordinate the orbitals are facing. That value is also given by M. That is also given by magnetic quantum number. And so this negative value doesn't mean that it is going to be high. It is going to be positive. I mean, directing towards the negative side. No, it's not like that. It no, not exactly. See, this -1. If we say that, if I say that it corresponds to Px, no, it cannot be like that. -1 can correspond to any of this. Again, 0 to corresponds to any of this. 1 corresponds to any of this. Okay, so it's all to just to give an indication that there is some direction difference are there between all the three orbitals. That's what you need to understand here.
Sir, what is Px, Py, Pz?
I'll tell you, coming to that. Okay, fine. So now we understood, right? So for every n value gives about information about orbits, L about subshell, and M about orbitals. Okay, now forget about S. S is okay. S is very easy because I have only one box, right? Now P has 3 boxes, right? Or 3 orbitals. Now these 3 orbitals have different names. Okay, the different names are nothing but Px, Py, and Pz. Now, what do you mean by this? P orbital along x-axis, P orbital along y-axis, and P orbital along z-axis is what it means. Okay, now I'll give you the shapes of them. Don't worry. P orbitals, I'm going to give you the shape, how it looks, all that. But for now, what you have to understand is P subshell contains 3 orbitals. And what are the names of the 3 orbitals? You have to understand that it is Px, Py, and Pz. Okay, right. Same way, D has 5 orbitals, right? Obviously, I'm going to have 5 different names. Okay, what are the different names? It's called dxy, dyz, dxz, dx squared minus y squared, and dz squared. 1, 2, 3, 4, 5. Okay, so what you have to understand here is that this d orbital is along x, y plane, right? This that there we talk about axis. We know, right? Obviously, if we have both the axes like this, we get a plane like this. Okay, so this dxy is in the xy plane. This is in the yz plane. This is in the xz plane. This is also in the xy plane, but little different. This is having only the z axis, but 3D. Anyways, don't worry about it, right? All you have to understand is the names, right? So for P, it is Px, Py, Pz. Y only 3 because I have 3 orbitals coming from the magnetic quantum number, right? And same way for D, I have 5 orbitals. D subshell has 5 orbitals. And what are the orbitals? dxy orbital, dyz orbital, dxz orbital, dx squared minus y squared orbital, and dz squared orbital. These are the orbital names. Okay, right? So this obviously S doesn't have anything like that. And for F, you don't have to know it. Okay, for P, Px, Py, Pz. For D, all the 5, if you remember, more than enough for R level. S obviously has nothing. So S has only S. That's it. Okay, because there's only one box or one orbital. Okay, right? Any questions, guys? Any questions anybody wants to ask me till now? Any clarity required anywhere? Okay, Fine.
Sir,
Yeah, tell me.
sir, like if we consider Bohr's atomic model or
Hmm.
Rutherford's atomic model, like they
Hmm.
all gave a specific diagram, right? In quantum mechanical model, like do they give any specific diagram about
Yes,
how?
they do. They do in the sense, but you will, even if I give you, it does not going to make any sense because it's all probabilistic, right? It's all in the waves, right? Say now I gave you a diagram like this, if you can remember, some diagram like this. Okay, say this is my K shell, right? Or I would say this is my, or I'll forget about it. Like actually, I'll give you the exact exact things, even though it is not required for you, right? Say if I write psi squared of x for one s orbital. Okay, now this is how the wave function looks. This is how it, I mean, there should not be any negative value because it is squared. I'm sorry. Okay, now if I write it for 2s, it is going to be something like this. Okay, so this is again psi squared of x, right? And this is my x values. Okay, well, don't worry about it. We don't have to go into the details, but answering your question, yes, they do give you some diagrams, but those diagrams are not what you expect it to be. I told you that everything is of waves. So this psi squared will help me find out what exactly is the type of wave pattern which I get for 2s or 1s or 2p or 3p or 3d, whatever it is. This, what to say, this type of wave pattern, how the graph looks, yes, that they will give. But how do you, like, if you expect that, okay, this is how the atom will look, that kind of picture you want? No, that picture is not available in this model. Okay, because it is all probabilistic, it's all waves. Waves can also overlap also. Say one wave and another wave can overlap also, right? So it will be a very distorted picture, even if you try to imagine it. Try to imagine, okay, whatever I'm trying to say, and if you try to, picture it in your mind, you are actually going to get a very clumsy picture, like a very, like I would say, a cloudy picture is what you will be getting. Okay, so but yeah, other forms of diagrams are available. Say this form of diagram is available. I will give you what are the shapes of this px, py, pz, all these d orbital shapes, how those diagrams are there. But if you expect it like, what Rutherford or Bohr or Thomson did, that kind of diagram, no, here we'll not be able to see that.
Okay, sir.
Sir,
Yeah, tell me, Kana.
sir, so electrons oscillate as well as revolve around the nucleus.
Oscillate as well as revolve. Yeah, correct. It's like how planets revolve around the Earth. They undergo revolution also and rotation also. Something like that. Yeah.
Sir,
Yes. Yes, Kana. Tell me.
sir, can you once again briefly explain about the dxy dy?
Yeah, sure. Right.
Okay.
Yeah. So what we understand now, do we understand that D has 5 orbitals?
Yes.
Why
sir.
D has 5 orbitals? Because L value of D is 2. This is what is D subshell. So M will have -2, -1, 0, +1, and +2. Right. So all of this -1, -2, 0, +1, +2 are 5 different orbitals for D. Right. So basically that's why you put 5 boxes. Right. Now each of these 5 boxes, just like, even though all are humans, we have different names, right? Like that, these 5 boxes are 5 different orbitals. Those names are dxy, dy, z, x, z, x1 minus y4, and z square. Nothing. These are the orbital names, nothing else. And like about this xy plane, yz plane, xz plane, you don't have to worry about it. Once I look at the diagram of how these orbital looks like, right, then you will be able to easily understand this. Okay, wait for it. I'll give you that in 5 or 10 minutes.
Yeah, okay.
Right? Okay. Anybody has any other questions?
Sir,
Anything? Yeah, tell me.
sir, if electrons were considered to be waves, are they transverse or longitudinal?
That's a nice question. So look at this. All electromagnetic radiations, right? All electromagnetic radiation, like X-rays, gamma rays are nothing but electrons, visible light, all these are transverse waves. Right? I think I forgot the definition of transverse and longitudinal. Transverse wave doesn't require medium and longitudinal waves requires medium. Is it like that?
In transverse wave, it will act, the energy transferred will be acting perpendicular to the direction of
Exactly. Then all these are transverse waves, because electromagnetic waves, if you check, they have three components. One is or I would say three different things will have three different directions. What are the things you have to look into? It is about the electric field. From the name itself, you can understand. You have electric component, magnetic component. So electric field, magnetic field, and at last the direction of propagation. Or if at all you want to call it as energy transfer, however it is, direction of propagation. Okay, now all these three are mutually perpendicular. Okay, all these three. Say if I can, if you're looking at my video, this is how I can represent. Say this way I can talk. This is one direction. Say this can be electric field, this can be magnetic field, and this can be the direction of propagation. Okay, you can understand all these three are mutually perpendicular. 90 degree, 90 degree, 90 degree. All these are mutually perpendicular. This is how an electromagnetic radiation will work.
Yes, sir.
Okay, right. You will study more about them in your 11th. There's something called as electromagnetic induction. You have a chapter. They start about this in your 11th.
So they didn't start.
Okay, they will start. At that time, did you have it in 11th or 12th? Okay,
Sir,
anyways, in 11th or 12th,
10th
you
or
study.
11th, sir, not 11th.
No. In 11th or 12th, either you will study in this year or next year you will study. Okay, right? Fine. So that is about the electromagnetic wave. And yeah, light, electrons, all of them are electromagnetic radiations, electromagnetic waves, and all of them will have three components, and all of them will be mutually perpendicular. Okay, fine. What is the time? Okay, we have 15 more minutes. Right. Fine. Now, what I can do is we have one more quantum number to see. Okay, there is the last one is my spin quantum number, if you can remember. Well, the 4 quantum numbers, very right. Right. So we completed principal, azimuthal, magnetic. Only spin is remaining. But before we see spin, I talked about the shapes of these orbitals. Right. Px will have one shape, Pz, Py, dxy, dyz. What are all the shapes? We'll try to understand. Right. How the shape looks. Right. Okay. That we'll see, and maybe in tomorrow's class we'll see what is about the spin quantum number. Now, okay, after you realize all the quantum numbers, now we have to understand how am I going to put the electrons. Now we know how many maximum electrons can be there, how many minimum electrons can be there. All these things we know, but how exactly are you going to do it? We have certain rules which you have to follow. Okay, so tomorrow's class will study about the rules. And once we know about the rules, then we'll directly go into the electronic configuration in terms of SPDF, in terms of orbitals. And with that, the chapter gets over. Okay, right? So for now, we will try to concentrate on shapes of orbitals. Okay, shapes of orbitals. Okay, right. So now, starting with S, right? Now remember that S orbital is always spherical in shape. Okay, S orbital is always spherical in shape. Very simple. I draw a sphere and I entirely shade it. Okay, this is entirely shaded. This is how S orbital looks. Okay, I would say this is exactly how one S orbital looks. Now, 2s orbital will be spherical in shape, but it will be little different. How it will be different? Let me tell you. It will be something like this. Okay, so this entire region is shaded. Okay, and this region is not shaded. Oh, okay. I'm sorry. This is not the way it looks. Wait, I'll try it again. Okay, so this entire region is shaded, and this entire region is shaded, but you see this, right? Right, that is not shaded. Okay, now what do you mean by shaded and what do you mean by not shaded is, if it is shaded, there is electron. The probability of finding electron is still there. Probability of electron is there, right? But when you find that this particular region is not shaded, Okay, now thus not shaded regions are what are called as nodes, where nodes are the places in an orbital where probability of finding an electron and probability of finding an electron is 0. Okay, what you have to understand is in this shaded part, electron can be present. Inside the shaded part, electron may be present. But in between these two, there will be a region where you cannot find electron. The probability of finding electron is 0. Okay, now that I can give a special place, special name to that place. That place is what is called as nodes. Okay, now nodes are present not only in S, so what you have to understand is one S orbital has no nodes. Okay, 2s has one node, right? Basically one place where I cannot find any electrons. Okay, so this is how the shape looks. Now what you have to understand is that s orbitals are spherical in shape, right? And 1s orbital will be a perfect sphere, 2s will be a little different sphere but still a little different sphere, 3s will be again different. Okay, and what you have to understand, there's something called as nodes where the probability of finding electron is 0. So
Sir?
3s, yes, questions? Yes, please tell me.
Sir, is nucleus a node?
Sorry?
Nucleus is a node?
Nucleus is?
A node.
No. Nucleus. Oh, obviously, nucleus is a node, but we speak about nodes only for places which are inside the orbitals. Are you able to get the point? Nucleus is entirely
Yes,
outside the whatever, right? Outside the shell itself, isn't
yes,
it?
sir.
But nodes we speak only for places which are inside the orbital, like this. Inside the orbital, I have a region which I don't have any electron. That's why.
Okay, sir.
Okay, right. So that is about s orbital. Okay, next, when I go to p orbital, orbital, right? Now p orbital, obviously p, x, p, y, p, z, there are 3 different things, but all of them are going to be dumbbell shaped. Dumbbell shape, like you use dumbbells for doing exercise, right? That dumbbell shape. Okay, but how the dumbbells are oriented is what is going to be different between px, py, and pz. Okay, very simple, right? P, so dumbbell shape, like this. Okay, anyways, if I draw px, right? Now, guys, the axis which you draw is very, 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 very important. My diagrams sucks, right? Anyways, I'll try to. Okay. Okay. Fine. So I told you, okay, this, I assume that this is y-axis and this is x-axis.
Sir?
Yeah, tell me.
Sure, shouldn't these all be shapes of orbitals?
Obviously, all these are orbital shape. Yes. Oh, I did write orbits. I'm so sorry. I'm so sorry.
Yes, sir.
Yeah. Okay. These are shapes of orbitals. Okay. Yeah. Good. Thank you. So yeah. So assume that this is x-axis and this is y-axis. So I'm talking about px. Okay. Now what you have to understand is the dumbbell, right? The dumbbell shape should be along the x-axis like this. No, not perfect. Wait. Perfect. Okay. You see, this is the dumbbell, right? Right. So the dumbbell will be pointing along the x-axis. Y-axis will have nothing. Okay. Now what you see is, I didn't draw it properly, but exactly at the origin, right? This is the origin. Maybe I'll use different color. Right. So exactly at the origin, again, you see there is no shaded region. This is shaded. This region is shaded, but in the origin, there is no shaded region. So this again is a node. Okay. And the node means what? Probability of finding electron is 0. Okay. Now, same way, if I can draw for py, right? Again, it's going to be dumbbell shaped, but look at how am I drawing this. This is my y-axis. This is my x-axis, right? Now, since it is py, the node, the dumbbell should point only along y-axis like this. Okay, right? So again, you see exactly at the origin, there is a node. right? This is again a node. Okay, right? Fine. Now, see, look at this. The shape of this node here, that is in the 2s orbital, what you saw, and this kind of node, what you see, are two different shapes, right? I'm talking about the shapes of the nodes itself, right? So what I'm trying to tell you is that nodes are of two types, right? One is what is called as radial nodes. The other one is what is called as angular nodes. Okay, one of the node is what is called as radial nodes. Other one is what is called as angular nodes. But we'll see it maybe tomorrow. We'll try to concentrate on the shapes today. But all I have to understand is there is the shape of the node here is different, and the shape of the node here is different. Okay, so we have only two types. Don't worry. Okay, radial node and angular node. What are these? We'll see in tomorrow's class. Okay, fine. So we know how Py looks. So maybe if I draw Pz, right? So Pz is going to look like this. Say, assume that all I have three axes, right? X-axis. I'd say, okay, this is Y-axis. This is X-axis. Say another thing will be coming towards you like this, right? So let me represent it like this. So for my this is my Z-axis. Okay, all these are mutually perpendicular. X, Y, Z are all 90-degree apart. Okay, so if I have to, now you have to specify, if you don't specify the Z, Y, and X, chumma you put a dumbbell, the diagram is wrong. The axis is very, very important. Okay, so now if I have to draw a dumbbell, this is how I draw. Please bear with me, dumbbell. Okay, this is a dumbbell along X-axis, sorry, Z-axis. Again, in the middle, you will see a node. Okay.
Sir, could you repeat, sir?
Yeah, what? Wait. Now, if I draw it maybe like this, Pz. Okay, so assume that this is my Z-axis and this is my X or Y-axis, doesn't matter because all of them are mutually perpendicular, right? So if I write Pz, I will draw the dumbbell like this again. But you can ask me, sir, what is the difference between this and this? Obviously, you see the lobes, that is the dumbbell, is pointed along Y-axis, but in this case, it is pointing along Z-axis. The same thing is only draw here. Here I drew all the three axes: X-axis, Y-axis, Z-axis. Z-axis in this distant way. So obviously, the lobes, that is the dumbbell, will point along the X-axis. Again, it is pointing along the X-axis because it is Pz. In Py, it will point along the Y-axis. In Px, see, it is pointing along the X-axis. That's what it means. Understood? Yes.
Yes, sir.
Okay, cool.
Sir,
Yeah, tell me.
sir, these are angular nodes, right?
Yeah, whatever we are seeing here, angular nodes, absolutely, yes, correct. And what we saw in your 2s orbital is radial node, absolutely. Okay, but we'll speak about it in detail next class.
Sir?
Yeah, tell me.
Sir, actually the graph which you have drawn is actually two-dimensional, right?
This graph is what I'm doing is two-dimensional, absolutely, yeah.
Sir, isn't it three-dimensional because there's Z-axis?
Yes, sir.
Obviously, but in the third dimension, you are not going to see anything. For example, I take say Px, right? So this can be Y or Z. Okay, but will it be? No, fine. And what I'm telling you is correct. It is only 2D, right? Because the third axis, either it is Y or Z, in those particular axes, you will see nothing, basically. That's what you have to understand.
And sir, I have a doubt, sir.
Hmm.
Sir, the lobes are three-dimensional, right?
Yeah, that's what. Like lobes are three-dimensional, no doubt about it. Maybe if you maybe you'll consider this 3D only because these lobes are like say bulging out. Correct. So maybe if it is just this axis, there should be a line only. But since I have a shape like this coming out, obviously, yeah, it should be 3D. Yes, it's not 2D.
Sir, so can we say that like the lobes lie in all the three planes?
Lobe, see, in this case, lobe is just a point, right? So point, if I have to speak correctly with respect to mathematics, a point has no dimension.
No, sir, I meant lobe, not node.
Lobe is there along all the three axes. Absolutely. Right. But majority of them, how they point along, which axis are they? This a main axis? That is my x-axis in case of px, y-axis in case of py, and obviously the z in case of pz. Okay.
And sir, can we determine the size of the lobe?
Oh, obviously. So if it is going to be 2p and 3p, there will always be some difference in the size. Okay. But that much detail we don't have to go into. Right. What you have to understand is lobes. These lobes are the regions where electron is present. Right. Wherever you don't have the lobe, obviously at the center, that means there is a node. That's what you understand. Shape, I mean the size, it will vary between 2p and 3p and 4p, go on. Like that will be varying. But not that much. You don't have to worry that much about it. Even the shape itself will be little distorted for 3p and 4p and all. You really don't have to worry about it. Yeah, but answering your question, the shape will be different. The size will be different. Yes. Yes. Okay.
Sir, could you repeat how the radial node looks?
Radial node is like this, right? So radial node, if I write it like this, it makes some sense. Say, okay, so this entire region is shaded. That means electron is present. But this, the smaller circle, right? This is my node. This is my radial node. Right?
Sir, then outside the sphere shape, it should be fully node, right?
See, that's what I'm telling. If you want to speak about node, it should be inside the orbital. Outside the orbital, obviously everything is a node, right? I mean, nowhere you'll find the electron. Orbital is the only place where you can find electron. But inside the orbital, there are specific points or places where you cannot find electron. There only you give the concept of node. You understand? Nodes are always inside the orbital, not outside. Okay. Fine.
Okay, sir.
So px, py, and pz. Okay, we have d orbital. I think we'll see tomorrow, people. Okay, d orbital's shape and what are the rules for electronic configuration. All those things we'll see in tomorrow's class. Okay. If you have any other question, you can ask me, or we can wind up. Anybody has any questions? Okay, fine. If that's the case, I think I will stop right here. Right, and we'll see tomorrow again. Right. Thank you so much, people. It was a wonderful class. We'll meet again tomorrow. I'm going to end it.
Thank you, sir.
Thank you.
Thank you, everybody. Thank you.